Okay, so the last speaker of today and last speaker of the whole role of algebra of this year's OSTEMS is James East from Western Sydney University. And James will be talking about transformation and representation of semigroups.
Okay, thanks, Mikhail, and thanks to you guys for coming to this talk. This is all joint work with these people here. And it's, in fact, an entirely COVID project. So this all began when we were all under lockdown. So we've not been talking to each other, just emailing. So I'll dive right into the idea of this talk. It's a fairly simple idea, I think. You basically, in terms of notation, we have a positive integer n. We write bold n for the set of the first n integers. And we're interested in the semigroup of all functions or all self-maps of this set. So this is called Tn, and it's the full transformation semigroup of degree n. And this is important because every finite semigroup embeds into some Tn, similarly to the corresponding result for groups embedding in symmetric groups. And because of that, we can ask the question, what's the minimum such n? So that's defined to be the degree of a semigroup, the minimum n such that S embeds into Tn. And this, of course, gives rise to a natural problem. If you have a favorite semigroup, what's the minimum degree of this? And this is not an easy problem in general, but it's a fairly natural problem, I think. So this was described as a dangerous question by one of the previous speakers. Why would you do this? Probably everyone here agrees that if maths is fun, then you should do it. Basically, if you have an interesting family of semigroups, then you end up with an interesting kind of combinatorial question. And it's generally quite challenging. Even if you take a relatively simple semigroup, it can be quite difficult to calculate its degree. One practical reason you do this is for computation. So for example, GAP has lots of good algorithms for working with transformation semigroups. So if you want to work with a new kind of semigroup, it's good to give it to GAP in terms of transformations, and the smaller the degree, the better. Another point that I only added a few minutes ago was the previous James in this session mentioned that if you look at all the semigroups of size n, and n increases, they basically become all quite boring, or in other words, 3 nilpotent. But it turns out that if instead you enumerate by degree, so you look at degree 1 semigroups and degree 2, then degree 3, etc., you'll see the same semigroups eventually, but in each bucket, they're full of much more interesting semigroups. So it's an interesting sort of philosophical point there. And of course, if this was a longer talk, I'd mention a lot of existing results by some of these people, but unfortunately I can't. I'll be mentioning some results, particularly by Easdown, and I should note that a lot of these results are about degrees of groups. All right, so this project itself started a couple of years ago when I was doing a simple calculation in GAP, pushed the enter key, and I was expecting to see the picture on the left and ended up seeing the picture on the right. This led to a little paper, 5 pages in experimental maths, which you can look up. It's just a pretty short read. And it basically sort of accidentally led to an upper bound for the minimum degree of a thing called a sandwich semigroup. And previously, the best that we could say about this degree that it's at most n to the n, and it turned out that completely by accident, I got this upper bound of 2n. And if n is 100, for example, we're talking about 200 rather than a Google or Google squared or something like that. So it's quite a surprising little result. But these sandwich semigroups are probably a discussion for another day. And today I'll be talking about some more simple semigroups that kind of these sandwich semigroups are built out of. So one of the collaborators on this project emailed me out of the blue several months ago saying he'd read this paper and he had some ideas for how to pin down the exact value of this degree, and the whole project started from that. So what are these simple semigroups? This is not simple in a technical sense, they're just sort of easy semigroups to describe. The first 2 are related, so I'll start with what's called a left 0 semigroup. That's just a set, any old set, and the product of 2 elements just always gives you the left element. So every element in this semigroup is a left 0. Okay, very simple sort of semigroup. A couple of observations. One is that every element is an idempotent. Okay, if you take x equals y in the product, you just get x. So these are examples of bands. Another point is that, well, the only thing that distinguishes isomorphism of left zero semigroups is the size. It doesn't take long to convince yourself that semigroups are the same, left zero semigroups are the same size or isomorphic. So there's really only one left zero semigroup of any given size. And of course, that leads you to the question, what's the degree of a left zero semigroup? And that was answered by David Eastdown, my PhD advisor back in the 90s. And I'll talk a little bit about how he computed that shortly. Then, well, yeah, the point is that, okay, we've got a whole family of left zero semigroups, L1, L2, L3, and if we calculate their degrees, we get an integer sequence. So if you have a nice family of semigroups like this, you get nice integer sequences. All right, obviously we have right zero semigroups where every element, every product just gives you the right element. And of course, we can ask what's the minimum degree of these things. Eastdown also calculated this sequence. And one obvious sort of question is, well, the semigroups are basically the same, right? Just sort of left-right duals of each other. Do we get the same minimum degree? All right, so two more kind of simple semigroups. One is a null semigroup. This is not where every element is a two-sided zero, because a semigroup can only have one, at most one, two-sided zero, but it's a semigroup where you have a zero element, and the product of everything is just zero. So the multiplication table just has zeros everywhere. Okay, this time there's only one idempotent, because if x squared equals x, well, x squared also has to equal 0. So x is 0. But then, of course, you know, we've got a null semigroup of every possible size, and we can ask what's the minimum degree of this. This wasn't previously known, so I'll talk about this later on. It's probably not known because people just, for whatever reason, didn't worry about it yet. But the last example I'm going to talk about is one that definitely people wanted to know the answer to, but hadn't yet been able to work it out. And that's the idea of a rectangular band. So here we've got a semigroup with two coordinates, and the product, well, the product of two pairs is kind of, you just ignore the middle two things. So you keep the left coordinate of the left factor, and you keep the right coordinate of the right factor. And if you stare at this for a minute, you realize it's basically just the direct product of a left zero semigroup, so AB equals A, with a right zero semigroup, XY equals Y. All right, again, every element is an idempotent, so this is another band, hence the name. And well, obviously we can ask what's the minimum degree of such a band. Now we have two parameters, so the size of the left zero semigroup and the size of the right zero semigroup. So these numbers form an array. Right, so to answer these questions, we have to think about transformations a little bit, and I'm just going to give you some sort of basic ways to represent a transformation. So we've all seen this idea of permutations. You list the numbers 1 up to n, and below you list where those numbers go. We can do the same thing with transformations, except because functions don't have to be permutations, there could be several things going to the same place. So in this example, which I'll usually just write using triangles, 1, 2, and 3 all go to 2. All right, so A1 is the set of all points going to x1, A2, everything going to x2, and so on. And associated with this transformation, we've got a few obvious parameters. We've got the image, which is just the usual thing, all the things that do get mapped to. We've got this thing called the kernel, which for today's purposes, I'll be thinking of as the partition of the set of n elements. All the things mapping to the same place are in the same block of the partition. So it's just the blocks A1, A2, and so on. And we've got this other thing, which is important, called the rank. That's the number R in this picture. It's basically the size of the image, or it's the number of triangles when you draw this picture. Okay, and idempotents were pretty important in all those examples we looked at before, so we'd just better think a little bit about what makes a transformation an idempotent. So if you look at this F here, imagine we were going to do F and then F and wanted the answer to be F again. So think about a point from the set A2. Okay, it maps to X2, but now that we do F again, well, X2 is up here, so it maps down to X3. So all of A2 in F squared actually instead of going to x2, which we wanted it to go to, in fact goes to x3. So this is not an idempotent. You basically have to make sure that, well, x2 had better be in the set A2, and this would better be the case for every I. So here is an example of an idempotent transformation. Every set maps to a point within the set. So you end up with triangles that sort of go down like that. All right. So let's think about left zero semigroups. What's the minimum degree of a left zero semigroup of a given size P? Okay. Another way to think about the same problem is, well, we're trying to calculate an integer sequence. Here's another integer sequence that we might want to calculate. And if we can calculate this one, then we can calculate the first one. So we say, all right, instead of fixing the size of a left zero semigroup, we fix a degree of a transformation semigroup and say, what's the biggest left zero semigroup that you can get in there? Okay. And if you understand the second sequence, then you understand the first sequence. So the minimum degree of, say, 1,000 element left zero semigroup is the smallest n, such that Tn contains a left zero semigroup of size at least 1,000. Okay, I'll have some numbers up in a little while that'll make that a little bit clearer. But the point is, we want to answer this second question. So let's consider a left zero subsemigroup of some Tn. Okay, call this semigroup L. The first thing you do is you show that within this semigroup, all the elements, all the transformations in L have to have a common image. And let's imagine that image is the set X, let's say. Okay. The other thing we remember is that every element of a left zero semigroup is idempotent. So we're looking at a bunch of idempotents with this fixed image. Okay. And if you think about what an idempotent with that image does, well, it has to map these points onto themselves, but you've got complete freedom as to where everything else in the set 1 up to n goes, as long as it goes to one of these points. So you've got n minus r points left over. They can each go to any of r given points. So there's a total of r to the power of n minus r idempotents with that image. You'd have to believe me on this one, I guess, or you can just check it fairly quickly later on. And well, interestingly, that only depends on r, the size of this set. So basically, if we maximize this value over all possible r's, we get the maximum size of a left zero semigroup. And so that's stated in this result of ease down. So you can calculate those numbers pretty easily, either by hand or with a computer. And then, as I said, if you want to work out, for example, the minimum degree of 1,000 element left zero semigroup, you just look at the numbers on this bottom row and you see that, okay, T8, the biggest left zero semigroup, has size 256, but T9 has a left zero semigroup of size 1024. So L 1000 embeds into T9, but not T8, and therefore its minimum degree is 9. Okay, that's good. What about right zero semigroups? The situation is kind of similar. So if we want to work out the minimum degree of a right zero semigroup, we can sort of turn this question around and say, what's the biggest right zero semigroup you can find in a given Tn? This time, if we consider such a subsemigroup, it turns out that elements have a common kernel. All right, so let's say the kernel is sets A1, A2 up to AR. So this is a partition. Every element is idempotent again. And so now what we've got is we've got a bunch of idempotents with this fixed kernel. So we've got A1, A2 up to AR fixed, and we just want to choose the X's. Okay, now the X1 has to be some element of A1, X2 has to be some element of A2, etc. There's this many ways to choose those things. They're all idempotents and they all happen to form a right zero subsemigroup. So what this is it's a product of numbers who add to n. Okay, A1 union A2, etc. is the set 1 up to n. So how do we maximize the product of integers with some n? Well, for a given r, this is maximized when the integers are almost equal. So they're all around about n over r. Okay, and by varying r, then we can find the maximum of these maximums, and it happens when almost all of the integers are 3. All right, so basically, the biggest right zero semigroup is equal to some small power of 2 times as big a power of 3 as you can. So you basically write n as the sum of as many 3s as possible, with the remainder, if any, being a couple of 2s. All right, so there's the values of that. If you look at the values of row n compared to lambda n, you see that in fact, Tn contains quite big left zero semigroups, but not so much big right zero semigroups. So the degrees of left and right zero semigroups are not equal. All right, what about null semigroups? This is the case where we've got a zero element and every product is equal to this zero element. So again, since there's only one null semigroup of any given size, we can tackle this problem by looking for the biggest null semigroup of a given Tn. This is where we had to think of some new ideas. We want to find a null semigroup of Tn with a given 0. That's got to be an idempotent. And the idea is you look at your idempotent. It looks something like this. For every kernel class of your idempotent, so for every Zi, you fix a Yi, it's a subset of this thing, and it's got to contain the image point. And then you look at all the transformations that do two things. First of all, they map each Zi into this fixed Yi, and they also map the fixed Yi onto the fixed element Xi. And if you think about composing this F with another thing that does basically the same thing, well, everything's going to just map down to X1. So the product of any of two of these things is going to be zeta. So this is a null semigroup with 0 zeta. It turns out that any null semigroup with this zeta is contained in such an N where you choose the subsets Y1 up to YR in some way or another. So the biggest null semigroup is going to be one of these things. You can work out what its size is by just saying, well, it's just determined by essentially the sizes of the Zs and the Ys. The freedom in defining an element like this is all in where you decide to send the elements of Z1 that are not in Y1, and you get this. All right. Then you do some mucking around with these things. It's basically a parameter associated to an integer composition, so a bunch of numbers adding up to n. Turns out that this is the biggest when there's only one of these blocks. Okay, and then whatever y1 is, call it k. This is going to be k to the power of n minus k. All right, and then we can maximize n by maximizing this value for all k's. So that gives us this, which, if you remember from before, is in fact exactly the same thing as we had when we looked at the biggest left zero subsemigroup. So there's this strange sort of equality between left zero semigroup degrees and null semigroup degrees, even though they're basically worked out in completely different ways. So this is sort of a mystery in a sense. But so we've got the same minimum degree of a left zero semigroup and a null semigroup. All right, the final example I wanted to talk about is sort of the more complicated example where we've got rectangular bands. So the question is, what's the minimum degree of a p by q rectangular band? All right, so we've got a left zero semigroup of size p, right zero semigroup of size q. We don't have to worry about when p or q equals 1 because that would just be a left zero semigroup or a right zero semigroup. Because there's two parameters here, we can't just say fix n, what's the biggest rectangular band you have? So we have to directly look at the degrees. So it might not seem like much of a step, but I'm going to call this thing beta pq. That's the smallest n such that Tn contains a p by q rectangular band. And then the main step is to introduce another parameter, r. So beta r pq is the minimum n such that a certain set that now has an r in it contains a p by q rectangular band. What is this dr thing? It's just the set of all transformations of a fixed rank r. The point is any rectangular band contained in a full transformation semigroup has elements all of a fixed rank. All right, so we've got these numbers that we want to calculate. And if we can work out all of these for every r, then beta pq is just the minimum of these numbers over r. All right, so imagine we've got a p by q rectangular band consisting of rank r elements in Tn. What we do is we take the set of all possible images of these things. All right, they're all transformations of rank r, so each of these things are an r element subset. And if you were in Marcel's talk before, you might think, well, okay, we've got a bunch of subsets of a set, we can form a graph or a hypergraph. The elements are the numbers 1 up to n, and each of these things are hyperedges. Okay, and because they're all r element subsets, this is an r uniform hypergraph. And I literally didn't have a picture for this before, but stole this from Marcel's talk. Thanks to him, he's not here now, so you can't complain. Okay, that's that. But we've also got the kernels. So we look at all the elements of our rectangular band, and we take all of the kernels. Okay, these are a bunch of partitions of the same vertex set into R blocks. And the miracle is that each of these partitions tells us a proper coloring of the graph. Okay, so a proper 3 coloring of this 3 regular or 3 uniform hypergraph is shown. Each hyperedge contains 3 vertices, and each of these 3 vertices has one of the distinct colors. Okay, now in this picture, we don't really care what the colors are. We just care that there's 3 of them and that each edge contains exactly one of them. All right. It turns out that the number of hyperedges is Q, the number of partitions is P. So we've got some connection between rectangular bands and hypergraphs with nice colorings. Not only that, but we can describe the elements of the band. I won't go into detail here, but every partition and every image gives rise to a unique idempotent. All right. So the summary of that is that if we've got a P by Q rectangular band of rank R elements, rank R transformations of degree n, we get a nice hypergraph with n vertices, Q hyperedges, it's R uniform, and we've got P unordered proper colorings. Conversely, any hypergraph with these parameters gives us a bunch of idempotents, but the problem is that it's not necessarily a semigroup. So we've got some kind of combinatorial connection. The question is, do we sort of sacrifice too much information with this? The nice thing though is that if there is any such hypergraph, you can always find maybe another one that gives rise to a rectangular band. So the full summary is that the degree of a rectangular band, a P by Q rectangular band, is the minimum of a bunch of numbers beta R defined as we did before, which have this alternate interpretation as the smallest number of vertices you need for there to be a hypergraph with the right number of edges and colorings. And then you do some mucking around with hypergraphs, and it's actually possible to write down exactly what this is. It turns out that you look at some logs, and we've got this parameter which sort of appeared before, which is the product of a bunch of numbers that are almost equal, so they're within one of each other, and who has a given sum. All right. The point of that is that these are actually very easy to calculate, and so the last couple of slides just have some numbers. I'm not going to dwell on these too much, but for example, the degree of a 10 by 10 rectangular band is 10. You can go a little bit further, and in fact, even way further. So the minimum degree of a billion by billion rectangular band happens to be 64. So what's interesting about this is, as the rectangular bands get bigger and bigger and bigger, the degree doesn't go up massively. All right, so that's where I'll stop. This is the paper, which hopefully will be appearing at some point on the archive. As I said, it sort of goes a bit further, and we're looking at sandwich semigroups, but these things come in for various reasons. And yeah, thank you for listening.
Thank you, James. Do we have any questions? Well, if not, then let's thanks James again. And yeah, thanks everyone for coming, and hopefully we get to meet next year in person, not just via screen.